All right, so in this section, we're going to be talking about normal distributions and standard normal distributions. Specifically, we're just going to kind of introduce the topic today, and then we'll go further and further into it as we go. And this is eventually going to lead into testing hypotheses and being able to look at studies and kind of determine the validity of those studies. So to start off, let's go ahead and define what a normal distribution is. A normal distribution is simply a continuous probability distribution for a random variable x. The graph of a normal distribution is called a normal curve. The normal distribution has these properties. And we'll go over the properties here in just a second, but let's go ahead and illustrate what a normal curve looks like. So a normal curve, we have our x-axis, okay? And the curve is going to kind of do a bell shape, all right? So it's going to look something like this. The peak up here is the mean. Okay, so this is the average of our graph. Okay, so the further to the right, the higher the average. The further to the left, the lower the average. Okay, and just like before, we have standard deviation. So let's say that this is a standard deviation to the right. Remember to write the standard deviation to the right is simply mean plus one standard deviation. And a standard deviation to the left, same thing, but we're subtracting a standard deviation. Everything we calculate is going to be based off of the rotation of the mean. So I could say that the second one, so another standard deviation would be the mean plus 2 standard deviations, or the mean plus 3 standard deviations, and so on. And I could do the same thing over here. I could say this is the mean minus 2 standard deviations, and this would be the mean minus 3 standard deviations, and so forth. Okay? And remember, to be unusual, it falls behind that second standard deviation, so either to the left or to the right of our second standard deviation. All right. So let's keep going through these conditions. So it says the mean, the median, and the mode are all equal. In other words, this does become a symmetric bell curve. So this side should look the same as this side of your bell curve in order for it to be symmetric. Okay? Then it says the normal curve is bell-shaped and is symmetric about the mean. So we have that. The total area under the curve is equal to 1. So if I were to add all of this area up, let's change colors. So if I were to add all of this area up, everything underneath the curve, we should add up to be 1 or 100%. Remember that the area under the curve represents that probability. Then it says the normal curve approaches but never actually touches the x-axis. So it doesn't matter how far out we go, this curve, this line is never actually going to touch the x-axis. It's going to get really, really close. In other words, the probability is going to get really, really close to 0, but it's never actually going to hit 0. So we always have a chance no matter what the x value is. And then finally, between the standard deviations, so between the first standard deviation, so between this and this, my curve obviously curves downward. Okay, so we have this parabolic curve where to the left and to the right of this curve, so to the left and to the right, we have an upwards facing. Okay, and notice that both of these hit at this. So this is called an inflection point. So this is an inflection point. Okay, so an inflection point is simply where it changes from a downward facing curve to a an upward facing curve. Inflection point. Okay, so and notice that both of these hit, and it will always happen this way in a normal standard distribution. It will always hit at 1 standard deviation to the left and to the right. All right, so let's go ahead and take a look at an example. It says, which normal curve has the greatest mean? So remember that the higher the mean, or the further to the right, the peak is, the higher the mean. The further to the left the peak is, the lower the mean. Okay, so what we're going to be doing here is we're taking a look at this graph and we're looking for the peak with the highest x value. So notice that the x value here is approximately 45, same with graph C. However, graph B actually hits right around 60. So the normal curve with the greatest mean is graph B. Okay, then we're going to take a look at the standard deviation. The standard deviation actually tells you how spread apart our graphs are going to be, so how wide the graphs are. So again, what we're looking for is the fattest graph. So the biggest standard deviation is the fattest graph, so visually the fattest graph. So notice that these are both graph A and B are fairly skinny. However, graph C is a fairly wider graph. So in other words, the data points are more spread out. Okay, so I would answer that graph C has the higher standard deviation. All right, so moving on, let's go ahead and take a look at another example. So in this next example, it says the scaled test scores for New York State grade 4 Common Core English test are normally distributed. Okay, and this is a key word. This is one that we're kind of looking for, is normally distributed. The normal curve shown below represents this distribution. What is the mean test score? We're going to estimate the deviation of this. We're going to estimate the standard deviation of the normal distribution. Okay. So let's start off by looking at what the average is. So we're going to try to kind of estimate what this average is. So remember that the average happens at the peak. And if we kind of just estimate, it's going to be approximately 300, or our test score is going to be approximately 300 on average. Okay. Now, to do the standard deviation, what we're going to be looking for is the inflection point. So taking a look at this is kind of hard to tell, but we can kind of estimate that maybe it's about right here. Okay, so everybody might have something slightly different here, but if we were to estimate, we're looking for those inflection points, so where it stops curving downward and where it starts curving upward. Okay, so our inflection points happen about 260 and 340. So if we were to think of this as the average, and this is the average plus a standard deviation, and this is an average minus the standard deviation, okay, notice that we're simply adding 40 and subtracting 40. Okay, so I would say that a rough estimate of what our standard deviation is about 40 points per test. Okay, so I want you to recall that the normal standard distribution can be calculated with a z-score. Okay, so we've talked about z-scores before. Z-scores represents the position on your graph, on your chart. Okay, so the z-score can be calculated as the value minus the mean divided by the standard deviation. Okay, the way we write that symbolically is the value minus the mean divided by the standard deviation. Okay, so let's go ahead and talk about another definition. So it says the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. The total area under the curve is still 1. So this is actually going to look exactly like this first graph that we talked about. However, the average in this case is actually going to be 0. And this is one that we will talk about quite a bit. All right, so let's go ahead and draw this out. So I've got this normal curve. Okay, and to be a normal distribution, the bell, or the top of the bell, has to be 0. So this is our average. And then our standard deviation is 1. So the average plus 1. So if this were 1 standard deviation away, it's going to be 1, 1 standard deviation way over here is -1. This would be 2, 3, -2, -3. So really our distribution looks the exact same, but this is a normal distribution. This is what we can use our z-values to interpret. Okay, and again, we'll talk about that later on. All right, so properties. The properties are pretty much the same, but the standard normal distribution says the cumulative area close to 0 for z-scores close to z equals -3.49. So in other words, if I go backwards, -3.5, and I go backwards, the probability of whatever that event happening is really, really close to 0. Okay, and it also kind of works for this one too. So if I go to +3.5, so let's say that this is 3.5, the probability for all of this stuff happening is almost 100%. Okay, because when we're calculating probability, it takes all the area to the left of this. So if I'm adding up everything back here, it's taking up almost the entire bell curve. Okay. The cumulative area increases as the z-score increases. So as our z-score gets bigger and bigger, so this is our z-axis, so as our z-score gets bigger and bigger, the area, or the probability of whatever that is, gets bigger and bigger. So that makes sense that if I were to calculate the area back here, okay, and then I were to calculate the area behind this blue line, the area in the blue area, or with the blue, actually has more space or more coverage than what the red does. And I'll explain more of that whenever I'm in class next week. All right. And then the cumulative area for z equals 0 is 50%. So in other words, because this is the average, right? So our average, that means that the area behind the average makes up 50% of our total area. All right. So using the table on pages A16 and A17, I'll show you guys how to use the calculator here in just a little bit. But using the table, we want to find the cumulative area that corresponds to the z-score of 1.15. Now, I do want to remind you that this always calculates. So it calculates to the left. So it calculates the area to the left. Okay, so if we were to ever ask what the area to the right of something is, we would have to subtract it from 1 or find the complement of that. And we'll do an example of that later on. All right, so a z-score of 1.15, the way we're going to do this is we're going to take a look at this z column here. Okay, so we're looking at these and we're looking for 1.5, and notice that it is over on page A17 right here. Okay, so right here, and then I'm going to look for 0.05 at the top. So 0.05 is right here. I'm going to highlight down, and then highlight across, and we're just looking for that intersection. And so the area to the left of I did this wrong. We were not looking for 1.5. We were looking for 1.15. All right, so it's right here to here. All right, so the area to the left of the z-score of 1.15 is, so probability of z equals 1.15 is approximately 0.8745. Okay. To calculate the area that corresponds to this one, okay, we're going to do the same thing. We're going to search for negative 0.2. So right here. Then we're going to look for negative 0.04, which is right here. And we're simply going to trace down and right and see where they intersect. So the area to the left of this is about 0.4052. And there we go. That's how you would use the table. All right. Now, using your calculator, this is going to better be explained whenever I get into class with you guys. However, it says we want to find the area of the standard normal curve to the left of z equals negative 0.99. Okay, so if we were to draw this out, okay, and I would suggest drawing this out. Here's 0. Okay, negative 0.99. It doesn't have to be perfect. I just kind of want to see where it is approximately. So negative 0.99. It's going to have to be to the left of this. Okay, so this represents the high, and we're going to use this here in just a second, but this is your highest value. And notice that your lowest value has no limit. So we're going to pick a really, really small number here. So using the calculator, I'm going to give you guys some steps. And I apologize that this is a little bit more disorganized than normal. I'm still struggling a little bit talking. Okay, so first thing you're going to do is go to second, vars. Then you're going to scroll down until you see normal CDF. Okay, and it's going to ask you lower, upper, the average, and the standard deviation. Okay, now for the average and the standard deviation, your average, because we're dealing with the z curve, standard normal curve, our average is always going to be 0, and our standard deviation is always going to be 1. And we'll talk about how these change later on, but for right now, it's just going to be 0 and 1. Okay, so the lower and the upper is what's going to change in these problems. Okay, so the lower is the furthest to the left this is going to go. And notice that this doesn't really have an endpoint. So what I'm going to do is I'm just going to pick a really, really small number. So I'm going to say negative, maybe 9, just put a whole bunch of 9s in here. Okay, it doesn't have to be exactly this. It just needs to be quite a few. Okay, the upper is going to be the highest value that it goes. So the cutoff, in this case, it's negative 0.99. When you hit enter, you're going to get that the area is approximately 0.161. Okay, so that's how you're going to use the calculator to do this. And again, drawing this out is the best way to kind of visualize what's going on. All right, so now it says find the area under the normal curve to the right of 1.06. Okay, so if I'm finding the area under the curve to the right of 0.16, so here's 0, here's 1.06, okay, we're looking for this area back here. Okay, so in order to calculate this, now we're taking a look, and this is our new lower limit, where our upper limit doesn't actually end. Okay, so when we're filling in the lower and the upper, the lower limit is going to be 1.06, and the upper limit's just going to be a really, really, really big number. So I could just, again, type in 99999, a whole bunch of 9s, and we should get, and again, this is just you checking, but you should end up with an area of about 0.145. Okay, if you put enough 9s in there, everybody should approximate to the same area. All right, the last example. This time it says we want to find the area under the standard normal curve between negative 1.5 and 1.25. Okay, so again, I'm going to draw this out. Okay, so I'm going to draw my curve. I've got 0 right here in the middle. It's going to be between these two values, so I know that negative 1.5 is about right here. positive 1.25 is about right here. So I'm looking for the area in between these two values. Okay, so this time, the lowest it goes, we have an endpoint, so we have lower, and then we also have a highest it goes, so this would be my upper. Okay, and again, I'm going to leave this part to you, but when you calculate, you should get an area of approximately 8.828.